Okay, okay. So good morning. My name is Sandro Varisi. As I told you, I'm going to be talking about my machine learning algorithm to predict protein binding sites. I've been doing this research at molecular modeling and bioinformatics group with Modesto.co. And let's get started. So yeah. So first of all, my model was my aim was to predict protein DNA binding sites using a machine learning algorithm based on experimental data and DNA structural features describing geometry and stiffness at the base pair level. So experimental data was taken from PBM based on a fluorescence experiment, and basically our goal was to find the binding site in a genomic sequence, a DNA sequence. So, okay, so let's start with the situation. So I don't know if you guys have ever done a machine learning, but most of the time, like the things you have to do is to clear the input. So it's clear for the machine to like get to know what's going on. So our input was here was at 35, was like a lot of sequences, around 40,000 sequences that were 35 like bases long. And we had the affinity value that was found out by subtracting the value minus the background. So we have like this somehow clear value. And okay, so the first problem we found was the sequences were really long. So we have to trim them because, you know, like the binding site is not going to be like probably 35 base pair long. So we have to find like something shorter. And we have to find something around, I don't know, 12, 10, 8. We really don't know what's going to be like, but we know it's going to be shorter. Like a protein is not going to bind equally around this part. Another issue we had was when we represented the values, like the affinities, well, normalizing them against the sequences, we found kind of like these two profiles. The first one, like this was really skewed between like the low affinity range and the high affinity range. We had like this whole separation. If you take a look, you can see that like the low affinity range goes from 0 to almost 24,000. It's like almost the whole part of it, while the high affinity range is like just this little spike. So in this case, if we try like to teach the machine how to like predict the binding site, it will go crazy because it will say, okay, so all of the affinities are going to be 0. It's gonna predict like constantly 0 because that's what it has as input. So we should like take this into account and try to like make something similar to this one, which is smoother. Having said that, the first thing we tried was to like, okay, so we're going to use the top sequences, the top affinities to generate this logo plot. I think you can see it, right? For instance, this one you can see like you have some spot here, which is not clear, but for the rest, you have some letters that are going to be like there forever. So we used this logo plot for first of all to trim the 35 mers into 12 mers. And we also use it for like weighting the machine learning. I'm going to explain it later. And also for undersampling and oversampling. I'm going to get there in a second. So yeah, in this case, the one we said it has like this kind of like skewed profile. We wanted to do two things. Okay, the first of them was to like generate more data around here to teach the machine that these data are the most relevant, the high affinity. And we did this by oversampling. Oversampling literally means to generate new fake data, but not in a random way, like more like generating something similar to what we have, but like in a way that's not the same. We did this by basically using this consensus sequence, this logo plot, and replacing one of the nucleotides by something similar. In positions 4 and 5 or even 10, it doesn't really matter if we change VA for a T or something similar, but we cannot change, obviously, 2. So in this way, we could use the consensus to generate more data and to have more information. And for the low range affinities, for all of this part, we had the undersampling that was basically removing in a smart way. And we did 4 things. First of them was trimming the tails, say, okay, from say sequence 5,000, we're going to remove it. We're going to say, okay, this is not relevant because maybe it's noise, maybe it's just something experimental mistake. We really don't know because the signal to noise ratio here is really, really low. So we need to improve it. And we also used the consensus sequence again to generate a score by sliding window and generating different scores for using the frequency metric, sorry. And we removed those that were not really nicely aligned with our consensus. We also removed them. Again, we removed high p-value sequences. If it doesn't match, we remove it. And finally, point 3, we have removing random values in equally spaced intervals. What's the meaning of this? So what we did was, okay, so we placed all the affinities in a line from 0 to 1. And we divide it into intervals. Say we have boxes. We have 5,000, 25,000, like a lot of them. What's the point of this? By using these boxes, we pick one point from each of the boxes. In this way, it's smarter than just removing data because we are picking some really low affinities, say 0.01, 0.02, but in a way that we don't have too many data. And by doing so, we get nice results. We also thought of using other algorithms. I don't know if you know KNN, K nearest neighbors, but this one still had like a lot of noise around here because low affinity is really problematic. So we thought, okay, so let's try with this and stick to this. And we got it, like it was a nice result. And we need to find basically the number of points we chose from division. That was one, number of divisions, number of boxes, and the boundary is, okay, so we're gonna take the points up from 0.5, down from 0.5, sorry, not more than that. Okay, and once we have discussed this, we're gonna go straight to the machine learning per se, the regressor. We used a random forest and we had these features. We basically had two of them. We had the presence, that was sequence composition, and the base pair parameters, basically structure. The data was collected from MD simulations for each base pair and each tetrameric environment using newly improved force field, PARM BSC1. I don't know if you know it. So what we did was using these features, we had the 12mers, the affinity, and what we did was just slide window, as you can see here, using tetramers and calculate the features, apply them for our tetramer, and get this matrix, the X matrix. Okay, here. So yeah, and in the end, we use the R-squared coefficient as a quality measurement. So we're finally going to go straight to the results. This is the matrix of correlation we found. We have three columns. We have the presence, average diagonal, and presence average diagonal. Each represents one of the features. This is the sequence composition, this is the structural, and this is a combination of the two of them. I guess you can see like this column here has more blue than the previous one. That means we have better correlations. If you can see here the heat map. So the result here states that using both sequence and structural features yields better results than just using one of them. What's the meaning of this? So in order to have a good prediction, we not only need to know about the statistics, about like say, okay, so the A shows up here 3 times, here 4 times, whatever, but more like we need to know the statistics and the physics about it, like also DNA structural features. Also, if you can see like the metrics, we have pretty nice results, like almost 80% of the data is over 0.5, which says it's not being random. And also around 60% of the data is over 0.70, which is really like sharp prediction. We have here 2 plots of 2 proteins that are in the high correlations. We have this one, for instance, CFP, that goes, okay, you can see here in the low affinity range, we have kind of like this cloud, which is still not really well predicted, sorry. But as you go up for high affinities, you see like the tendency curve is like the straight line we want to see in the correlation plot. What's the meaning of this? What we're training the machine to do is like, okay, if you see a high affinity spot, you're going to match it, like you're going to have it for sure. And if it's low affinity, well, you're going to try to do your best, but you know, some will go good, some not that good, but you know, in their overall result, it's like to have this really nice correlation plot. And again, for the AR is the same thing. However, not everything was nice and clean when we were doing the model. And for some proteins, namely 4 of them, we had this plot that was really scattered, really like spread out. And basically this corresponds to the proteins that had at first this profile. I don't know if you remember the one with the smooth curve of affinities. So it made us think, so what's going on here? Why does our model not work here? And that's what we're trying to figure out now. So if we focus on the affinities for like, say, medium high, up from 0 to 1, we have kind of like this plot in which we have the number of sequences found per interval and the normalized affinities. And we see this distribution. So the first thing we notice is, okay, so skewness is important because if the profile is sharp and like really skewed, we know how to predict, but if it's not, we have some issues. And then we have this thing. So it may lead to think like we have something like bimodal, maybe something goes down and then goes up. Maybe we have more than one binding side. Maybe the binding side is not exactly placed in a particular tetramer, maybe it's like spread out, or maybe we have a smaller k-mer. If our binding site was like a tetramer, you can find it in like a lot of 12mers. That would explain why we have like this smooth curve, because, you know, like if the tetramer is found in like many 12mers, each 12mer will participate equally or like in a pretty important way to the affinities, and overall the result will be like that. So just to sum up, our model has shown out like we predict really well for like a lot of proteins, namely if it has like this skewed profile, but still it fails for like some proteins. That's what we're trying to tackle now. And our work is like, right now we're trying to figure out if we have more than one binding site or whatever. And basically that's it. Thank you so much for your attention. If you have any questions, please let me know. Thank you.
Many thanks, Sandra, for the nice presentation. So please, if you would like to ask some questions to Sandra, please remember to click on the raise hand button. I am checking now the list of attendees to see if someone has a question. Okay, so it seems for the moment no questions. Okay, many thanks, Sandro.
Thank you.
So we will move to our next speaker. She's Alba Carvalho, and she has been doing her research stay during summer at Patrick Alloy Research Group, the structural bioinformatics and network biology. So please, Alba, if you would like to share your screen. And thanks.
Good morning. I hope you can all see the screen. So I'm going to present you the job I've been doing this summer in the structural bioinformatics and network biology lab. And what I've been doing is I've been building a signature similarity tool. But first of all, I'm going to explain you a little bit of the theoretical background of what I've been doing. The structural bioinformatics and network biology group developed the chemical checker, which introduced a new way of characterizing bioactivity data. So what they do is they characterize this data as multidimensional vectors that we are going to call from now on signatures. So what they studied is 25 relevant aspects of a small molecule characterization. They divided it into 5 levels, as you can see here in this grid. Each one of the colors represents one of the levels that are at the same time subdivided into another 5 levels. So at the end, what we have is 25 relevant aspects that we can study. And these are called the chemical checker spaces. So for each one of these spaces, what we're going to get is a 128-dimensional vector that is called the signatures for each one of these spaces. We can study then small molecules for one of these spaces, or we can study for several of them by stacking the vectors horizontally. So at the end, we have a wide range of parameters to study. However, in the group, what they did is they calculated the signatures for all of these spaces for nearly 800,000 compounds. But sometimes we might want to know which are the signatures for molecules that are not in this database that is stored in the chemical checker. And for that, what they also created is the signaturizer, which is a tool that can infer signatures for any given compounds using neural networks. So this is going to be a prediction, and this prediction comes along with an applicability score that informs us of the reliability of this prediction. So the idea of my project was to develop a tool to perform similarity searches in the chemical checker. What we are going to get is some query molecules as an input, and then accompanied by an applicability threshold. Also the number of neighbors that we want to calculate for each one of these query molecules. And they also have the opportunity to select the chemical checker space in which to perform the search. We can work with the individual spaces or with the global of all of them. So we were stacking all of the signatures to study the global one. The idea is to get which are the nearest neighbors of these query molecules. accompanied by the Euclidean distance, because at the end what we are doing is calculating Euclidean distance from the signatures of the query molecules to the signatures of all the molecules that are in the chemical checker database. And this comes accompanied by an empirical p-value that I'm going to explain a little bit later how we calculated it, and also with the applicability score that I mentioned before. So the general idea was to compare any given molecule to all the molecules that are in the chemical checker database. So the tool works in the following way. At the beginning, once we have the query molecules, we're going to get the signatures of these query molecules. Then we are going to perform a nearest neighbor search. Once we have this nearest neighbor search, we are going to draw the distance distributions in order to retrieve the p-value. And finally, once we have all of this, we're going to stack it and we are going to show it as a result. This tool, we built it also in a web page that I'm also going to show you at the end. First of all, the available data that we had were the signatures for the nearly 800,000 molecules that are in the chemical checker. What we did is that we calculated them with the signaturizer, the tool that I mentioned before. And we also had the list of the INCHI keys for each one of the molecules that are in the database, and the applicabilities of all the prediction for each of the individual spaces. As I mentioned before, we were working with individual spaces or with the global of them. So whenever we needed the applicability for the global, what we did is the mean of the 25 chemical checker spaces. So once the user inputs a query molecule in SMILES or in INCHI format, and he selects a chemical checker space, what we did is that we applied the signaturizer in order to get the viactivity signatures. That is a 128-dimensional vector if the space is a singular one, or a 3,200-dimensional vector if we were working with the global of all the spaces together. Once we had that, we needed to perform a nearest neighbor search. The idea was to calculate the Euclidean distance to all the molecules in the chemical checker. So we could do so manually and then sorting by increasing order, but this took a lot of time. So what we decided to use is FISE, which is the Facebook Artificial Intelligence Similarity Search. It's an algorithm developed by Facebook Artificial Intelligence Group. And what it does is that it builds a data structure called index that can be stored in memory, and it can pre-calculate the distances given a data set with which we're going to work, and it can perform a very fast search. So there are a wide range of indexes for which to choose, but we decided to choose the flat L2, which is the exact Euclidean distance search. It's as if we did the Euclidean distance from each one of the query molecules to all the molecules in the chemical checker database, but it only does it a little bit faster, well, much faster than what we were doing if we did it manually. So we calculated this index for each one of the 25 chemical checker spaces and also for the global one. The problem here was that the global index was super big for the computer to load it each time we needed to use the tool. So we looked for other FISE indexes that use a technique called product quantization, but these indexes were not useful as they didn't care about the order here. So you ask for the 10 nearest neighbors, but they didn't give you the neighbors ordered. And in our case, we needed them with an order. So what we decided to do is to perform a principal component analysis to reduce from 3,200 to 600 dimensions on the global. And then to this one, we calculated the flat L2 index, and we stored all of this in memory. So each time the tool was going to be used, it will load the index and perform the nearest neighbor search. Then, in order to retrieve the p-value, we needed to build the distance distributions for each one of these spaces. We selected 384 random molecules from the chemical checker database. So you might be wondering why 384 random molecules. So the answer is this formula you can see here. This is the formula for the sample size. Whenever we had a big universe of molecules, with this formula, we just calculated a 95% of reliability, and it tells us to choose nearly 384 molecules. So we are going to have a reliable representation of what is happening in the chemical checker database. So we chose these 384 molecules, and for each one of them, we computed the distance to all of the molecules that are in the chemical checker database, and we stacked all the distances together, and we built the density function As you can see here, this is the typical shape. This one is for the global, but we did it for each one of these spaces and for the global. So at the end, what we got is 26 different distributions. From there, we could retrieve the p-value. And we did so by establishing some p-value thresholds, for example, 10 to the minus 5, 10 to the minus 4, and so on. And for each one of these spaces, what we did is we associated this p-value threshold to the corresponding distance. So at the end, what we are having is not the exact p-value, but just like the upper threshold for each one of the distance we are calculating with our nearest neighbor search. And we calculated so for each of the 26 distributions. So this is useful because each time you don't need to calculate the distance distributions for each one of the query molecules that might or not be in the chemical checker. And you don't need to load the pre-computed distributions because you already have this correspondence between the p-value and the distance, and this is very easy to compute and very fast to compute. So this is the complete tool, and then here you can see a little summary of how it works. We get a user input that goes to the signaturizer, and then to the nearest neighbor search. Also from the chemical checker database, we train the indexes of the FICE search, and we build the distance distributions. And from here, we get the applicability, the empirical p-value, and the nearest neighbor search. And we can have a result that will look like this. We built this tool into a web page that I'm going to show you, and we are going to also prove it. Here, this is the web page. I hope you can see it now. So as you can see, well, it's all linked to the chemical checker web page. It has a small section in which, well, now it's not working, but it had a small section in which you could see all the information about the tool. And I think I copied the molecule. So we are going to try with this one. We are going to, for example, select 5 neighbors and a given space. And it takes a little bit of time, but not too much. And at the end, what we are going to get is a result like this. Here is our input molecules, and here are the neighbors. If you click on them, it will direct you to the chemical checker database. You can also see the shape of the molecules, distance, the p-value, and the applicability that is given. And well, it has a lot of functionalities. I actually didn't know anything about web page programming, so I've been playing with that a little bit. And this is what I've been doing during this summer. And this is it. I hope you have enjoyed it. And I also would like to thank all the structural bioinformatics and network biology group and the IRB Barcelona for the opportunity that they have given me.
Many thanks, Alba, for the nice presentation. So I see that one hand was raised during your presentation, so I will just mute. So Salvador Aznar, you should be able to speak.
And I don't know if you can hear me now.
Yes. Yes.
Yeah, thanks. Yeah, no. It was, in fact, you have answered already. My question is just that I had it right at the beginning in terms of trying to understand what was sort of like the signature, etc. of what you're doing. But you've answered it already, so it's fine. It's a very, very interesting work.
Thank you.
Yeah, the thing, I mean, it probably would be nice. I know it's not the common thing, but do you think it would be possible that while we're having the presentations, that somehow we could ask questions and through it, or you prefer to have it more like in the standard format, no? That the person talks and then we ask questions at the end? Because I think in some of these presentations, it might be interesting to be able to like have a clarification during the talk. You know, otherwise maybe there's a risk that we don't end up understanding, you know, some of the stuff that are being explained.
I think, Salva, anyone can interrupt at any point in any way. So I mean, this should be fully informal type of. It is equivalent to a group meeting. So
that's what I meant exactly, to have it sort of like the equivalent of a group meeting. Yeah. But for that, basically what we would still have to do sort of like to raise a hand, no?
Yeah.
Okay.
So then Alba will give you the word.
Okay, great. Thanks.
In fact, I had a question. Can I ask the question, Alba?
Yeah, sure.
Oh, yeah. I mean, it was a beautiful work, Alba. So congratulations, great work and great presentation. It's amazing. I was wondering when you showed the example, yes, you put molecules that have a very similar to the structure. So what do you capture that you won't capture with a standard similarity measure type of thing and standard k-means type? So what kind of things are you capturing that you didn't capture before? With this clustering, these files that I didn't know the method, but seems to be very powerful, at least based on what the web page explains. So what have you find that is not that is surprising and that you can move to other spaces is discovering something about similarity in functionality that was not predictable based on the standard measures?
So the thing is that in the chemical checker, what they had before, they had this similarity between molecules that are currently in the chemical checker. The ones that I've also shown as example are currently in the chemical checker, but this introduces a way that if you find a new compound and you have these miles and you don't know anything about this compound, you can give it to the tool and it will compare with all that is in the chemical checker database because the signatures are inferred. So what you can do is you can see for any given space what is similar to your compound, even if you don't know anything about it. But at
So
the end,
you infer in the other spaces based on the similarity in the chemical space.
Yes, like you use the signaturizer, which is the tool that was already built. I didn't build it myself. It was already when I came to the group. And what it does is it uses neural networks and it will infer a signature for any given space for a given molecule that is not in the chemical checker by comparing it to a trained model. So once you have that, you can perform similarity searches with the current data that is experimentally verified, which is the data that is in the chemical checker.
Okay, so thanks a lot.
Yes, there is one more question from Patrick Aloy.
Hello, can you hear me?
Yes.
Okay, very good. Now this is just a comment for Alba and for Modesto. So Alba, maybe Modesto got confused because you used the A1 space that is pure to the chemical similarity. So if you run exactly the same example, but using any other of the bioactivity spaces, maybe Modesto will see clearly what you meant.
Yes, I think I can do it.
So just run B4 or D1 or whatever you want.
Okay.
So Modesto, what Alba is going to run now is looking for compounds that are similar, not in the chemistry, but in the bioactivity with ibuprofen, for instance. So B4 is the target space. So these are molecules that share targets, not necessarily the chemistry.
Exactly. The first one that we see is the same molecule because they are in the chemical checker, but then you can find different ones.
That's very cool. Yeah. So congratulations, nice.
Thank you.
Okay, so I will be presenting a coarse-grained model for chromatin dynamics. I'm David Faragil, and I've been working at the Molecular Modeling and Bioinformatics Laboratory, working with Juan Pablo Arcón and Modesto Orozco. First, I would like to introduce this project. The main goal is to design an algorithm that models coarse-grained chromatin dynamics. There's a bit of a gap between molecular mechanics and the mesoscopic scale. There's a lot of room for different approaches in the coarse-grained aspect. And in this project, we have revisited the work of Jürgen Walter, where a similar model is developed using helical coordinates and Monte Carlo simulation. This method is very efficient. The helical coordinates and Monte Carlo simulation are very efficient methods, but it doesn't scale really well, as particles that are far apart aren't really related. And we really want these to be related. That's why we rebuilt this algorithm using Cartesian coordinates. In this algorithm, interactions with distances are better understood because since everything is in Cartesian coordinates, distances can be calculated in the traditional way. Then distances between bases that are far apart do not pose any problem. This has some issues. It makes the algorithm slightly slower and a bit more convoluted, but we have been working to make it the most simple, but still maintaining this cohesiveness in the coordinates. And specifically, we are working on this project because we will have experimental results that highlight interactions between separate parts of the fiber. Then we really need to be able to work with these distances even when the beats are far apart. About the methodology of this project, we have designed an algorithm that will be based on elastic network models, which we will discuss in a moment, and which allows to simulate chromatin fibers in this coarse-grained approach. The algorithm will always take an initial configuration of the linker DNA fiber, as well as some parameters of equilibrium regarding the nature of the DNA, as well as some notions about the environment. And then we'll simulate the dynamics of the particles, giving the trajectories for the whole fiber, both nucleosomes and the linker regions. And lastly, this software has been built using standard C. So the elastic network model associates its nitrogenous base with a bead, and then these beads are the particles that are considered for this elastic network model. The energy for this model is the one which you can see here, which is elastic potential. In this energy, the K represents the strength of elastic potential. L represents the distance between two given beads, and L0 represents the equilibrium distance for a given base pair. Then we consider a cutoff distance such that this elastic network model is only considered for the closest neighbors. In this picture down here, we can see an example of a linker, and I've highlighted in blue a bead. Then in orange, we can see the opposing bead in the other fiber. And then in red, we can see, in this case, 4 beads in each direction, which are the beads that are affected by the elastic network model. We consider that further than this, there is a large decay in energy, which we call the cutoff distance. This is why we stop considering them for the energy that affects this blue particle. And lastly, the integration for the chromatin dynamics is integrated using the velocity roulette algorithm, which we have considered is the optimal for the kind of processes that we need to account for. Then we also add some Brownian movement to the model. For this, we generate Gaussian random collisions, and this allow for some freedom on the movement of the fiber. Mainly, this aims to model collisions with a solvent. And the displacement is applied smoothly along the fiber to maintain the structure. In this case, what this means is that whenever a bead is hit by a collision, we apply this collision to the neighbors, so that again this displacement is smooth. In this case, we might apply it to all its neighbors that are considered in the elastic network model. Another of the main keys of this algorithm is nucleosome reconstruction. The elastic network model is applied at every linker independently. Now we can see here an example of 4 linkers with 3 nucleosomes. And then we consider the nucleosomes as rigid bodies that move uniformly. Then we apply a strong energy restraint, at the end beads to keep the structure. In this case, the end beads represent the 4 last beads of every linker. There's there are big restraints within these 8 bits, which keep the structure of the overall chromatin fiber, and then these 8 bits can be used as a reference to rebuild the nucleosome. In this case, we can see a comparison with this is before the reconstruction, and this is when the nucleosomes have been rebuilt. Lastly, we have to consider exclusion distance and some amount of electric potential. In this case, we model it with the vehicle. Both of these fulfill very similar roles. For exclusion distance, we account for bits from different linkers. Since they move independently, we need to account for when they might be getting dangerously close. So after a threshold, the bits will start repelling each other, preventing collisions. This basically means that they cannot be over each other. And this is modeled with this exclusion distance notion. And lastly, the vehicle potential is an electric potential that again regulates how close charges of the same sign can get. And charges of the same sign can never collide, regardless of how strong their forces might be. And specifically, the energy for the vehicle potential is this one, where kappa and epsilon are some constants of the environment, and QA and Q2 are the charges of the nucleosome. Sorry, I think I didn't mention it. I should have. The vehicle potential is applied to nucleosomes. Nucleosomes have large electric charges that interact with each other. Electric potentials are somewhat disregarded in this algorithm. It's part of the simplification that we choose to do, but we really need to account for the electric potentials within the nucleosomes, and Q1, Q2 are the charges of these nucleosomes, and R is the distance between the nucleosomes. And here I put an example of this function. It's just as an example of the type of interactions that we want to force in the vehicle potential, as well as on exclusion distance. Forces that are negligible for relatively large distances, but as the particles get close, they really go up to infinity very fast. And now, lastly, I wanted to show some trajectory results on one example of the trajectories of the chromatin. Here at the end, we can see some of the results of the Brownian movement, how it shakes in a rather unexpected way. But as we can see, since it's smooth, it keeps the structure. And here we can also see everything that we have been talking, working together at the same time. And lastly, as a follow-up work, the basis for this model has been built and programmed, and it works properly. It's performing as expected for short fibers up to 3 nucleosomes, like the one that we just showed. And lastly, the balance between the different energetic terms, mainly elastic, Brownian, and electrostatic, needs to be studied carefully using principal component analysis, even though the constants are derived from other works and they are mostly accurate. We still need to be more careful with how they actually relate to the movements. And well, overall, there is room for refining the model, though some trade-offs need to be made in terms of performance. Specifically, we could add some other interactions. Again, the model would be more refined, more accurate. But again, we are looking for a coarse-grained approach, so it's important to keep this as a simplified model that allows to do this kind of midterm approaches. That's it. Thank you for your attention. If you have any questions.
Many thanks, David. So please, if you have any questions, use the raise hand. So if you don't have any questions for David, many thanks, David, and we will go for the next presentation by Giovanni Alexander. He has been doing his research stay at Tony Gabaldon Group, Comparative Genomics. So whenever you want, Giovanni, you can share the screen.
Yes. Can you hear me?
Yes, perfect.
And do you see my screen? The full screen?
Sorry, Giovanni, you have the presenter's view.
Yes, exactly.
Yeah, I know.
You can switch.
Okay. Okay. Let me 1 second. Screen 1. Okay. Now?
Yes, perfect.
Okay.
Thank you.
Well, hello everyone. My name is Giovanni Risco, and I'm going to explain to you what my project within the comparative genomics groups was about. First, I will try to explain the main concepts within the project, then the objectives, then the procedure, the results, and finally we're going to go through some of the conclusions. Before getting into detail with metaphors and the quest for orthodox concepts, it's important to remember what homology is. So let me give you a brief reminder about it. So as you may know, sequence homology refers to those genes that share a common ancestor. There are two types of homology, orthology and paralogy. And the main difference between them is that orthology comes from a speciation event, while paralogy comes from a duplication event. If you see here, this image, we have gene A in black as a common ancestor, and after a duplication event, we obtain two genes with identical sequences and within the same species. These are called paradox genes. However, after a speciation event occurred, the two resulting genes are not identical anymore, and now they belong to different species. This is what we call orthologous genes. You see here. And what is interesting about this is that while paralogy is often followed by functional divergence, orthologous genes tend to conserve their function. So if we identify them correctly, we can infer a function among different species. The thing here is that as accurate prediction of orthology has become a central task for many analyses in comparative genomics, there is a growing number of algorithms and resources to address this problem. These are only some of them, and therefore now there is a need to compare them on a common basis. This is how the Quest for Orthodoxy Consortium was born. It aims to simplify and standardize the ortholog predictions by providing a reference program and a web server for continuous orthology benchmarking. This way, the Quest for Orthodox initiative offers a variety of comparisons that will help the users to figure out which is the most effective method for the type of analysis that we want to carry out. Among all these methods, metaphors, which stands for meta-phylogenetic-based orthologs, serve as a public repository of phylogenetic-based orthology and paralogy predictions. It integrates phylogenetic information from different sources, such as PhylonDB, Ensemble Compara, Farm, EGNOG, among others. I think that currently there is about 13 different sources. And Metaphors was developed a few years ago by the Comparative Genomics group. Now that we understand these concepts, what do we want to do with them? So as you can imagine, it's not as simple as submit the ortholog predictions to the Quest for Ortholog service and obtain the benchmark results. The data needs a pre-processing step for being executed in the benchmark service, since it will ensure beforehand that only predictions among valid reference proteins are provided. Thus, the main objective of this project is to develop a pipeline that automatically performs this pre-processing by first filtering the data, therefore avoiding mapping issues and biases due to the difference in input data, and secondly, providing a valid input for the Quest for Orthologs server. By valid input, we mean that it should have only orthologs and only those that are among the reference protein. And of course, in a accepted format by the Quest for Orthologs. Then we are going to test the pipeline by submitting a metaphors orthodox predictions input to the course for orthodox and perform a benchmark and then study these results. In order to achieve these objectives, we follow the next procedure. First of all, we need to have on one side a reference proton retrieved from the quest for orthodox, and on the other side we have to have a metaphors database which should have the homology predictions and also the protein sequences about all the sequences within within metaphors. Once we have them, the first step consists of mapping the sequences from the reference proteome with the sequences available in the metaphors database. In this step, we look for identical sequences, and we will get a percentage of match that shows us how many of the sequences within the quest for orthodox are also in the metaphors database. The idea here is to have as many sequences as possible, because the higher the match, the more accurate the mentor will be. At this stage, if we already get a high match, we could continue forward with the next step. But most of the time we won't, because there used to be many proteins for which the sequence has varied or it's been updated or whatever. So we need to perform a blast to retrieve those sequences. So if we already get a high match, it's done. We go to the next step, which is filtering the orthologs. And in this step, the idea is to only have orthologs, and only those that have a match in the quest for orthologs. This means that only those proteins that we accepted, only those proteins that we accepted in the previous steps. Finally, we export these orthologs predictions either in a typical tab delimited text file or AuthorXML format, which are the accepted input formats by the quest for orthologs. We submit the input to the quest for orthodox service, and it will take care of the rest. It has a workflow, and we will run that workflow, and we will see the results. Well, now let's move on to the results we obtain with this pipeline. As said before, we first need to retrieve the necessary data sets for analysis. In this case, the reference proton that we used was from 2018. Which is not the last one, but it's actually the currently recommended one. It is made up of 78 species. Most of them are well-studied model organisms, and others are of high interest for my medical research and phylogenetic. Regarding metaphors, we didn't use the last data set either. Instead, we used the data set from 2016. Which cover more than 1,000 species and more than 170 million of homologies. But we encountered some problems with this data set. We're going to cover that later. And we're waiting for the last data set to be ready in order to run again the pipeline and obtain the final results. So we should take the following results as preliminaries, or even as an example to show you some of the quest for orthodox output. Taking this into account, let's get into the results analysis. On the one hand, we have the pipeline's output that let us know the statistics of the input we're going to provide to the quest for orthodox data. In this case, we got 85% of total proteins match, which may sound a high number, but it's a bit tricky, and we will see it later. Also, we provide more than 12 million pairwise ortholog predictions, which means out of the 117 million homologies, which means that we really did filter the data. Why did I say that 85% was a bit tricky? Well, it's basically because it represents the total match. It doesn't show us the individual matches. If we see the graph here, which represents the protein match of each species with its corresponding reference protein, which is the whole species. These are the 78 species from the reference protein. We will note that most of the species have a match above 90%, those highlighted in blue. And however, there are some of them, almost a quarter of the total data set, that have a match below 90%. And especially, there was some of them, for instance, Giardia intestinalis, which roughly reached 4% of maths, or even Cryptococcus neoformus, which has as a 32% of maths. We can't allow this to happen because we can end up in biased results. We suspect that something is going on with the sequences of these species. We are currently working on that, and we aim to have this solved for the next data set. Nevertheless, we continue with the analysis of this input, though we know in advance that we won't get good results. But anyway, as I said before, these are just preliminary results. We can start with the species tree discordance for Eukaryota, which is the one shown here. This test assesses the quality of orthology predictions by comparing gene trees built from predicted orthologs with the underlying species phylogeny. We can see here in the graph that it is highlighted with an arrow, the best scenario, which in this case is a high number of completed tree samplings and a low Robinson fold number. And in this case, for metaphors, we have quite a low value of Robinson fold value, but we didn't have a high number of completed tree samplings, so we can't claim good results here. We are expecting to have we're expected to have low coverage, but we didn't expect that such low coverage. The next, yes, this one. Another test we're commenting is the gene ontology conservation test. In this case, based on the predicted ortholog genes are assigned goal terms, and then compared to true annotations. This measures the effect of orthology predictions when applied to functional annotation. In this case, metaphors, which is here, gets a low number of orthologs, just as before, but in this case, it's pretty much the same as the other orthology databases. So it ranks very average in this test. Well, this is all the tests I'm gonna show you, because there are other few of great importance, but we decided to postpone them until we have the last data set. To conclude, I would like to remark that we are currently working on the metaphors database, so we can increase its coverage in some of the species that, as shown before, match very low, and then run again the pipeline. And well, that's why we should wait for the last data set to draw final conclusions. Finally, just say that although submission to the portfolio was part of this project, its main result is a pipeline, which is meant to be run as any other program in a Linux system. The programming language used was mainly Python, and all the code can be found in a repository of in GitHub in the Development group. But it's not public so far, but it will soon. Well, before finishing, I just would like to thank Tony Gabaldon for letting me be in his group despite all the circumstances, Marino, Lucia, and Manu for the help throughout the project, and of course to the Maths4Life programs for letting me participate in this opportunity. Thanks you all for listening, for your attention, and if you have any questions, just ask me, please. Thank you.
Many thanks, Giovanni. So is there any question for Giovanni's presentation? Okay, so it seems that there's no question for you. So many thanks, Giovanni. And so we'll move forward to our next presentation and last one by Kim Lopez. She has been doing her research stay in Modesto's laboratory. So please, Kim. Okay, perfect. You have already shared the screen. Many thanks. So whenever you want.
Okay. Hello, everyone. My name is Kim Lopez, as has just been said. I've been working in molecular modeling and bioinformatics group led by Dr. Modesto Orozco. And I'm sure you must be quite tired because it's been over an hour, but I hope that you're all up for a last 10-minute presentation about my project. So what I've been doing is framed by another project conducted by a PhD of my group called Jürgen Wolfler. who David has mentioned before, and his aim was to represent DNA conformations at base pair step level, so coarse-grained models and low computational cost. What he did was take the atoms of the DNA molecule, and instead of letting them move in the three-dimensional space, he conceived the base pairs as little planes that could move in what we call helical coordinates, so 3 translations and 3 rotations. And by simplifying the movement of the molecule like this, of course, he lost a little bit of accuracy, but the computational cost was much lower. So he could even put this algorithm in a web server for everyone to use. And the only inputs needed for this code were some parameters from molecular dynamic simulations and DNA sequences. And he did some Monte Carlo sampling. That's why from now on I'll call this code MC code. And then he could construct different DNA structures. I won't go very further into this. He then did some backbone reconstruction, but it's not important for what I'm going to explain, so we'll leave it here. And with this code, he could not only compute free DNA structures, but also constrained DNA structures, such as circular DNA. And the linear DNA, the free DNA, worked very well, and the group published things about that and everything. But the circular DNA had some problems. This is a typical output of the circular code. And as you can see, there are certain kinks and certain areas where there's a high accumulation of tension. And this is very unrealistic for DNA behavior. So my project was to try and work with this code to try and smooth the outputs. And instead of looking into the circular code, I looked straight into the linear code because we thought that maybe the problems were in both codes. But as the circular one has algorithms that are very displacement sensitive, we thought that maybe we could just look straight into the linear code, which is simpler. And we worked with a mini ABC library, which consists of 13 different DNA sequences that have all the unique tetramers. So you can construct a complete theory working with that. And the problems we saw were the following, which more or less account for the same problem in the end. We saw that the MC code computed higher end-to-end distances than the MD simulations. And the fluctuations on this code and the Jurgen model were also greater than the ones in MD simulations. And lastly, when I conducted PCA analysis, the eigenvalues of the principal directions were also greater in MC simulations than in MD simulations by a factor of around 2 on average. So all of this showed that we were probably allowing a higher distribution of structures in our code than in MD simulation codes. So our hypothesis, our way of explaining why all of this happened was the following one. So far, it had been thought that a certain movement in a certain base pair, a certain movement of the helical coordinates was independent of the neighbor ones, of the following ones and the preceding ones. But if that were not to be true, if a significant correlation existed between interhelical parameters, then we could account for these problems. Why? Because that would mean that we would be deeming different DNA conformations as equally probable, when in reality, they would not be equally probable at all. Actually, some of them would even be practically impossible. And by thinking they would be equally probable, we would be oversampling. So that would account for the higher fluctuations, the higher PCA values, etc. This was followed by an extensive study for my part in data analysis in these correlations. And we ended up with these figures, these graphics that are not yet finished, but these are the correlations of different pairs of base parameters depending on the distance. And of course, this is too much data, but if we just cut to correlation greater than 0.2, then we can focus on these 5 combinations of parameters and distance 1. And if we restrict ourselves to distance 1, and we try to look for the difference between different tetramers to see whether there's a different behavior in different tetramers, then we get to this kind of graphics. This is just a sample of them, of course. And the results were really, really promising because the higher correlations that we saw here corresponded to the higher fluctuations that we saw in our code. And also, if we see here, for example, in the AG1, the AG-centered ones, and this is the different combination of parameters, there is a certain regularity in the behavior of purines and purines, for example. So these results must not be random. There must be some theoretical explanation for all of them. That's what we thought. Lastly, I ended up working a little bit with bimodality. This means that normally now we understand the different distributions of the parameters as being Boltzmann average Gaussians, not simple Gaussians. So the models are not harmonic. What we wanted to see was whether if we were in a certain mode of this compound Gaussian in a certain base pair, if it corresponded well to a single mode of the next or the previous base pair. And I haven't done it thoroughly yet, but so far, roughly, my rough calculations have showed me that this is true, as we had been expecting. And when we have a simple Gaussian distribution, then what we observe is a displacement of the Gaussian. So all in all, I'm going to continue working in this project, and our intention is first to try and create a solid basis of all these results, clearing up non-significant correlations first, and then ensuring the statistical robustness of the results by working with other libraries instead of only mini-ABC. And then most likely trying to link everything with backbone configuration to see whether backbone turns can account for weaker or stronger correlations. And of course, moving aside from this theoretical part, we also want to try and implement these results in our code. So we want to develop a full non-harmonic model with this kind of Hamiltonian, just as the one we had, and taking into account these compound Gaussian distributions, as I just said, but also replacing our current stiffness matrix that looks like this with 6 rows and 6 columns for a larger one that also has stiffness constants for bases that are a distance 1 and doesn't take into account distances greater than 1, as I said before, because we have to cut somewhere. Of course, the computation of this matrix is no easy task, and we still don't know exactly how we are going to implement this in our algorithm specifically, but we're confident because the results have shown to be promising. We know where we want to get, which is always a good sign, and we think that not only this will improve our own outputs, but also the results are significant for anyone who wants to compute DNA molecules at this accuracy level. And having said that, I hope I have made myself understood and that you have found it as interesting as I do. By all means, if you have any questions, please let me know, and thank you very much for your attention.
Many thanks, Kim, for the nice presentation. So are there any questions for Kim? Okay, thanks again. So now I would like to hand over to Modesto Orozco, who will say some final words. Many thanks.
Okay, yes, to say all of you, thanks a lot. Very impressive presentations. So all of you have done a great job, and not in the best possible circumstances, but you know, the really impressive. How robust, how much have you done in a short period of time. And so thank you for agreeing to give this presentation, and thanks to all the attendees. We have had in the order of 40 people all the time, so this is a good signal of the interest of your research. So thanks again, you guys, and we'll keep in touch.